distribution of galaxies. There's something interesting about the distribution of them. So you can go into that data set and you can say, what is it? What is that distribution? Quite remarkably, it is predicted by the theory of inflation. So you can compare the two theories. So we can do that. By the way, I just thought I'd show you, this is another impression of that data set, just to give you some sense of the scale. So you see at every point here is the measured position of a galaxy. Over 2 trillion, by the way, 2 trillion galaxies in the observable universe, and we've mapped a reasonable percentage of them. And you see that there's this kind of strange web-like structure. It gets referred to as the cosmic web. So what's happening there? What does it tell us about our theories? Well, one way to look at the prediction, or to understand the prediction of inflation, a very beautiful way, is the theory essentially predicts that the origin of those little fluctuations in the density of matter in the early universe is kind of like taking a handful of pebbles and throwing it into the surface of a pond. So imagine I do that, handful of stones, throw them into the surface of a pond, what happens? The prediction of the theory is that it's like the stones all hitting the surface of the pond at the same time. Very important prediction. They hit the pond at the same time. So what does that look like, that pattern, if you look at it later on, at some time after you've thrown the stones in? It's like the Big Bang. You see a series of concentric circles. You see water waves going out from the position every stone hit the surface of the pond, so you'll see overlapping circles, sort of interlocking circles on the surface of the pond. The prediction of the theory of inflation is the same. So essentially, it says that if you look into that big data set and you look carefully, you should see circles on the sky on which it is more likely to find galaxies. It's a direct prediction. It's a remarkable thing. So that cosmic web is essentially interlocking circles on the sky caused by this initial sort of hit, the universe being struck essentially at the end of inflation through the Big Bang. It's an incredible prediction. So what we do in that data set is we make what's called a correlation function, which is essentially you take a galaxy in the sky in the data set and you open your field of view out until you see another one. You say there's a pair of galaxies. You take another one and you make there's a pair like that, a pair like that. So you're trying to pair them up to see if there's some predisposition for them to lie on circles in the sky. And you can plot that. And this is the graph. It was made very recently. So essentially, this is the distance between galaxies, and this is the so-called correlation function. So if there were no correlation, it would be smooth, but you see there's a peak in the data from that data set, which is telling you, yes, it is true. It is true that it is more likely to galaxies to pair up at a particular distance on the sky. So there are circles on the sky as predicted by the theory. It's a quite remarkable thing, beautiful thing. Now, I wanted to, because I'm running out of time a little bit, I wanted to, let me end now with that remarkable prediction, but let me wrap up by reading from the end of Feynman's book. It's a remarkable thing, I should say, that we've been able, this little sort of civilization we have on this little planet, to discern that, to even begin to have it's almost hubristic, isn't it, to say we make a prediction based on ideas of what happened before the Big Bang, when the universe was subatomic in size, essentially. The observable universe, I should have said, in these theories, grows from something a billionth of the size of an atomic nucleus. When quantum mechanical fluctuations end up getting written across the sky and seed the formation of galaxies, then we make a prediction and we look at the universe and it says, yes, you seem to be on the right track. It's an incredible thing. All coming from that period, that sort of cascade from an original idea of Newton's genius and then Einstein's genius, and then that period of being uncertain and checking and checking and checking, driving the idea as far as you can, and you end up with a theory that is predicting things that happened before the Big Bang. Let me tell you how Feynman wrapped up his theory on the value of science. I mean, this is the value of science, one value, that we can speak with any authority at all about events that happened in a subatomic sized universe 13.8 billion years ago is a remarkable thing. But here's how Feynman summed up his idea of the value of uncertainty in science. He said, at the end of his essay, we're at the very beginning of time for the human race. It's not unreasonable that we grapple with problems, but there are tens of thousands of years in the future. Our responsibility is to do what we can, learn what we can, improve the solutions and pass them on. It's our responsibility to leave the people of the future a free hand. In the impetuous youth of humanity, we can make grave errors that can stunt our growth for a long time. This we will do if we say we have the answers now, so young and ignorant as we are. If we suppress all discussion, all criticism, proclaiming, "This is the answer, my friends, man is saved," we will doom humanity for a long time to the chains of authority, confined to the limits of our present imagination. It's been done so many times before. It is our responsibility as scientists, knowing the great progress which comes from a satisfactory philosophy of ignorance, the great progress which is the fruit of freedom of thought, to proclaim the value of this freedom, to teach how doubt is not to be feared but welcomed and discussed, and to demand this freedom as our duty to all coming generations. Thank you very much.